So welcome back to NEET CBC. So today we will be discussing stereochemistry, that is very important for your biotechnology preparation. There will be at least one question from this particular chapter. Now first of all I will show you what are the types of questions which were appeared in the previous exams. First of all, look at this question. We have a question from 2021 and 2025 also we have, and even 2015 here we have, and next 2020. See, all these questions are very easy, you can solve within seconds. Okay, I will show you how can you solve these questions. First of all, let me tell you what are the things we need to focus here. In this chapter, see, first of all you need to understand the word stereochemistry part first. See, basically you know the term and you are much familiar with this term isomer. What do we mean by isomers? Compounds having same molecular formula but they differ in their, if they are differ in their structure, we are calling it as structural isomers. But there are some compounds having same molecular formula and same structure, but they differ in the arrangement of atoms in the three-dimensional space. Arrangement of atoms are differ. Those isomers are called as stereoisomers. So now isomers classification, first of all we have two types. If they differ in their structure, we are calling them as constitutional isomers or structural isomers. And if they differ in the three-dimensional space, spatial arrangement of atoms. For example, if you observe, I am writing a carbon with 4 different groups. Four different groups means hydrogen, like methyl group, and one deuterium, and something like ethyl group here. So there are 4 different groups are not around this carbon. So what is the hybridization of this carbon? Tell me first of all. It is sp3 hybridized. Okay, if it is sp3 hybridized, we know geometry will be tetrahedral. If this is a tetrahedral hybridization, then these 4 groups will be like this. The tetrahedral geometry, I hope you know that it will be looks like this in 3-dimensional arrangement. Okay, so now D, deuterium, which is above the plane I can say, and ethyl group is below the plane, and within the plane we have hydrogen, carbon and this methyl groups. Okay, so now what happens is, if I say this is one isomer, the stereoisomer of this will be having the different arrangement of this D, E, ethyl group, whatever might be. So now in the isomer, the stereoisomer of this compound, deuterium will be below the plane. It means how do they differ? Structure, everything is same, but 3-dimensional arrangement of atoms are different. Then those isomers considered as stereoisomers, right now, right. So now these stereoisomers are of different types. Isomers which are just formed by rotation of bonds. See, here I have a molecule like this, having a bond, CC connection is there. So if I rotate around the CC bond, what happens? See, hydrogen, methyl groups are there now like this. So by rotation what happens is, like you are catching wheel of one of a vehicle and you are rotating another wheel. So now what happens? We will get different arrangement, spatial arrangement of these groups or atoms attached here, right now. So isomers which are formed just by rotation of a bond are considered as for any molecule, the number of conformational isomers possible, if someone asks you, you should say it as infinite, because if I consider I am itself as a molecule, so by just a small change in the angle of my hands or my legs or whatever might be, we will get one different structure now, different force now, so that will be considered as one conformer. Like that, by rotation of even small degree of angle also will get different number of conformer. So conformations possible for any ethane molecule they will ask. What will be the answer? Infinite, because 0 degrees to 0.5 degrees will give one structure, 10 degrees will give, like that different number of possible structures are there. Now when it comes to configurational, see there are 2 terms. One is constitutional, it means they differ in their structure. Simply you can say structural isomers. They might be differing their functional group, or they might be differing their parent chain. Like that, those comes under constitutional. Already we have covered few days back. Okay. Now here stereochemistry, we have particular stereoisomer. One is conformational, one more is configurational. I am going to cover each and every question that were asked from stereochemistry part from last 10-15 years. Okay, in this session. Okay, next configurational isomers means these are of two types. One is geometrical, another one is optical. So these isomers, I will tell you what is this optical isomerism. Just hold on, just look at these terms. Okay, so now before going to further discussion of these configurational isomers, let us wind up with this conformational isomerism first. Okay, so now look at here. There is a question asked the difference in the energies of eclipse and stagger conformation of ethane. See the word where you have here conformations. It means those structures are conformers of this ethane formed by just rotation of bonds. So ethane means, how can we write? CH3, CH3. Now there are different ways to indicate this. The simplest one I am saying here, carbon 1 and carbon 2. Okay, now I am saying Newman projection. What is that? Newman projection to explain these conformations. See, this carbon I am indicating as a dot, this first carbon, and second carbon I am indicating as a circle. Is this fine? Okay, and first carbon what we have? 3 hydrogen atoms, like 1, 2, 3, and second carbon also we have. So you can place that hydrogen like this. So what does it mean by what we are showing here? See, this is an ethane molecule if you consider, one end one carbon and this end one more carbon. Now you are seeing this molecule in this way. So the back carbon, if you want to see this back carbon, this should not be present. Then only you can able to see, because they are exactly back to each other. It means if we indicate this first carbon as a dot, second carbon as a circle, then we can able to imagine properly. So this kind of projection is what? Newman's projection. What is that? This representation is there now. Newman's projection. Okay. So here what you need to know is, see, on first carbon one hydrogen is there, like this hydrogen is there, and second carbon also we have one more hydrogen. My index fingers are indicating hydrogen. See, if you are seeing this, you are only able to see the first hydrogen atom on the C1 carbon. Right now, the second one is behind that. Okay, so whenever we have like this, the angle between these is considered as dihedral angle. Angle between these two CH hydrogens are what? Dihedral angle. So when the angle between these two is 0, we can say the structure as eclipsed conformer. What is it? In eclipsed conformation, what is the angle? Dihedral angle? 0. So the angle here will be, theta will be 0. Is this clear or not? Okay. So now, by rotation of 60 degrees, what happens? Keep that, this center dot as it is. Try to rotate this circle, like C2 carbon. Now what happens? 60 means, see, this is 120 degrees. It will comes in between this, like this now. Okay, again 60 degrees if you rotate, this hydrogen comes here, back to this. Again you will get eclipsed conformation only. Again 60 degrees, one more structure. So if the dihedral angle is 0, we can call it as eclipsed. What is that? Eclipsed. If the dihedral angle here is how much? 60. This is considered as staggered. What is that? Staggered conformations. Now, what are the eclipsed conformation angles, you tell me? 0 degrees, eclipsed. 0, 120, here it will be 60, and 120 here, next 180 here, 240 here, 300 here, and 60, again 360 means nothing but 0. So these are the values you should remember. In the exam they will ask these values also. What are the angles of eclipsed conformation of ethane? What are those? 0, 120, 240. You can remember this value. Now, in eclipsed conformation, hydrogens are back to back now. So they will be having flat pole interactions, like repulsions will be there. So it means it is less stable. Which is more stable conformation of ethane? Staggered. Okay? Okay. Now, if it is more stable, its energy will be lower and its energy will be higher. Based on this, we have a question from this concept. The staggered conformation, the energy difference between eclipsed and staggered conformation of ethane at 25 degrees Celsius, they are saying. Okay, so remember, at 25 degrees Celsius, the energy difference between eclipsed conformation and staggered conformation is 12 kilojoules. How much? 12 kilojoules. Now they are asking these values in terms of calories. So I will give you the relation between calorie and kilojoules. So 1 kilocalorie, you can remember 4.2 kilojoules. Using these, we can able to calculate. So I have given 12 kilojoules, then how many kilocalories? X value you can get, that is nothing but 12 by 4.2, that will be around 2.7 we have now here. So that will be our answer. Is this clear or not? So its energy profile diagram will look something like this. See, what are these higher representation here with higher energies? Potential energy is higher, so these are eclipsed. These are lower energy, means staggered. Energy difference is kilojoule per 12 kilojoule per mole. Okay, so this will be the energy difference between staggered and eclipsed, or you can say nearly 2.7 or 3 kilocalorie per mole also, same value you can say in this way also. Okay, is this clear or not? And remember these values which I have discussed, staggered conformation values, they will ask eclipsed conformation values. Okay, right. This first question is clear now. Next, we have one more way of indicating the conformations when it comes to cyclohexane. Okay, cyclohexane means what we'll think generally, it will be having a structure like this. This will be the structure of cyclohexane. Now, in reality, cyclohexane exists in chair form. How it will be? Like a chair form. Okay, so in this chair form, why it is existing in chair form? Because if I represent in this manner, the bond angle deviations are negative here. Okay, more bond angle deviations are there. Because all carbon should be sp3, means bond angle should be 109.5 degrees. But in this case, it is not 109.5 degrees. That's why it is existing in more stable chair form. Okay, so in this chair form, there are two positions. How many positions I am saying? Two positions. One is axial position, one is equatorial. How can you identify this axial equatorial means? You know this coordinates representation now? If along this axis, you can say axial bond. Okay, it means I am writing one bond here and one more here. Which is axial? Above the bond, like above line is axial. So this is axial, this is equatorial. Like that, on each of the 6 carbons, there will be axial position, equatorial position. So this will be axial, equatorial, and this will be axial. Again here, I am indicating this will be equatorial, this will be axial. Again here, axial, equatorial. Here also, axial, equatorial. Here also, equatorial, axial. Okay, is this clear or not? Right. So this kind of scenarios, I mean in cyclohexane, on each carbon there will be 2 hydrogens, right? So these 2 hydrogen, one is axial hydrogen, one is equatorial hydrogen. Whatever I am explaining, this will be at lower temperature only. If temperature is raised, what happens? Kinetic energy increases now. Therefore, this hydrogen will keep on shifting here and there. Therefore, we cannot differentiate axial equatorial hydrogen at higher temperature. It means this axial equatorial concept will be at lower temperature only. Even if we see the spectrochemical data, this difference in axial equatorial hydrogens will be seen at lower temperature but not at higher temperature. Okay, right. So now, look at this compound, what they are saying. Which one of the following isomer is thermodynamically more stable for the given cyclohexane with 2 methyl groups? 1,4 dimethyl group is given here and 1,2 dimethyl is given, 1,3 it is given. See, I am writing like this. This is simple cyclohexane. Now I can place methyl group. What is the name of this compound, you tell me first? This is cyclohexane, 1 methyl, 2nd methyl. 1, 2 dimethyl cyclohexane. So I can place these two methyl groups either in axial positions or in equatorial position, or one axial, one equatorial, or equatorial axial. These are the possible ways. Now whenever we have alkyl groups, try to place them in equatorial position. Where I am saying? See, there are equatorial axial, no? Try to place them in equatorial position. See, I can place this equatorial position and here equatorial position like this. Okay, sir, how can we define equatorial axial means? I will tell you the all structures here. Just write all the structures. All which like see here, what is this? Otherwise you just tell me here whether it is axial or equatorial. Equatorial. This one also. So what are the positions? 1, 4 EE. Okay, what about this? 1, 2, 3, 4. 1 axial, 4 equatorial we have. And what about this? Both are 1, 1 AE. And what about this? 1 equatorial, 3 axial. So try to place the given alkyl groups in equatorial positions. Therefore, repulsions will be less. Okay, that interactions will be less. That molecule will become more stable. So which is having equatorials here? So that will be more stable. Is this clear or not? Okay, when we have alkyl groups, always remember, here I am showing you one more question. For this question, I have given explanation also, but for more understanding purpose, look at here. In the exam, they won't mention in that way. I am going to represent in some other way here. Like this they will mention. Tell me, there are two methyl groups. One is above the plane, one is below the plane. Or I can represent them. Both of them are in below the plane or both of them are above the plane like this. Okay. If both attached substituents are within the same plane, with same plane, we can say them as cis isomers. What is that? If they are having different planes, trans isomers. Okay. So write the chair form first. After writing chair form, one methyl group above the plane now, you put that above. One is below now, second position, so put below. It means like this we can write. If I rotate, if I flip this 180 degrees, what happens? These positions become inverted. It means axial becomes equatorial, equatorial becomes axial. Right now, so flip 180. Like this it will become. So tell me which is more stable, I told you? Equatorial, equatorial. Between 1 and 2 structures, which is more stable here? 2. So this is the perfect way of representation of this 1, 2 dimethyl cyclohexane, which is transform. Is this clear or not? Yeah. Other ways, see, this is a pure concept. Other ways, if you want, if you are getting confused, I will tell you one table. You just go with this. See, we have two possibilities. Either it can be a cis form or it can be a trans form. So we have 1, 2 position and 1, 3 position and 1, 4 positions. Right now, 1, 5 is nothing but again 1, 2 only. That cannot be 1, 5. Okay. So based on this, now tell me 1, 2 if I have, I should represent them as A, E or E, E. In trans, I can place them as AE, AA or EE. If it is 1, 3, cis becomes like this. First you remember this first line, based on you can do everything. So again, here it will be opposite, A, E, E. This will be A, E or E, E. Again opposite. It is nothing but 1, 4 is nothing but like 1, 2 only. Same representation. It will, cis means A, E or E, A. This is A or E. This is a way of representation. For example, I am giving you Tell me, what is the best way of representation of this 1,4 dimethyl cyclohexane? Cis or trans? Same planes, na, both of them. Cis. Cis means A, E or E, E. So just you can write this cyclohexane. If it is equatorial, this should be axial. If it is axial, that should be equatorial. Is this clear? Now, if these attached groups are very bulky groups, always place that bulky group in equatorial position. Which position? For example, tell me, how can I write this? Cis form. Cis form 1,3 cis means what I told you? E. Okay, it means both should be either axial or equatorial. But see, this is very bulky group now. Try to adjust that bulky group always in equatorial position. It means write the structure first. Okay, so if I place 1,3, so 1, 2, 3, if I mention like this, so equatorial position is like this, and here 1, that's it. This is a way of representation, yes. Okay, sir, always why only equatorial? Can we have any other cases which has axial position also? Means yes, axial position is possible when the molecule contain hydrogen bond. This is what you need to know here. See, for example, cyclohexane having OH groups at 1,3 position. See, 1, 2, 3. I can go from this position or like this also, 2, 3. See, I am placing OH here and OH here. Now what happens? Between this oxygen and this hydrogen and this oxygen, there will be hydrogen bond. Or one carboxylic acid group might be present here. See, now hydrogen bonding is there. So in this case, axial position you can place. That will be the most stable structure. Okay, this is the extra information I wanted to give on cyclohexanes. So bulky groups means which position? That's it. Okay. Now tell me, this molecule is there. See, 2015 they asked number of equatorial hydrogens in the given structure. Tell me. Number of equatorial hydrogens in the given structure. See, till now I have explained one cyclohexane ring. Now it is in the condensed form. So just write in this way. And I have given one trick. If it is above the plane, keep it bond as above line. And axial is occupied. Equatorial will be one this chain again, like this. And this is below the plane means you write hydrogen downside. And this will be connected like this. Now on each carbon there will be 2 hydrogens and 2 positions. One is axial, equatorial. Now count number of equatorial hydrogens they are asking. Each carbon you represent H, H, like that. Tell me. See, 1, 2, 3, 4, 5, 6, 7, 8. 8 equatorial hydrogens are there. Because these 2 positions already alkyl groups are there, these equatorial positions are not empty now. So remaining position all of them are having 1 hydrogen which is in equatorial. And how many axial hydrogens in this molecule if I ask? 10. Because 8 common, these 2 more. So 8 hydrogens are in equatorial and 10 hydrogens are in axial. Okay, clear now? You can able to identify. See, what about this position? What is the name of this position? And what about this? Equatorial. Like that, If there is no substituent on this carbon, means definitely there will be 2 hydrogen, one will be in equatorial, other in axial. So 1, 2, 3, 4, 5, 6, 7, 8. 8 positions are free. It means in that 8 positions definitely 1 hydrogen in equatorial, 1 hydrogen in axial. Okay, and these 2 are extra axials. Clear now? Next. Next. We have one more concept called optical activity. What I am saying? Optical activity. Before learning this optical activity, we need to know something about chirality or chiral centers. So first thing is chirality. So what do we mean by chirality? See, in the simple words, I can say chirality means handedness. What I am saying? Handedness. I have like 2 hands we have now. So if this is the hand, I am placing a mirror here. Its mirror image will be my left hand right now. So now you take this right hand and keep it on its mirror image. Are they superimposing? Like, are they merging? No. See, index finger, little finger, this is not merging. So this concept is called non-superimposability. What I am saying? If the compounds are having non-superimposability, then those are optically active. Once again tell me what is optical activity or chirality means? If 2 stereoisomers are not superimposable, we can say this activity as optically active. Or in other ways, like in simple words, I can say chiral carbon. What is this chiral carbon means? Carbon must contain 4 different groups. An sp3 carbon must contain 4 different groups. See, I am writing A, B, C and one D. Okay, now what is its mirror image? If this is a mirror, see, now this C which is below the plane becomes above the plane in its mirror, right? B and A, D, like this we will be writing. Okay, now if you take this molecule and if you keep on that, it won't superimpose on it. So these 2 are what? Optically active compounds, non-superimposable mirror images. So these 2 are optically active. Okay, so for optical activity, what is the criteria I am saying? Non-superimposability. What is that? Okay, so now look at the question what they are asking. Before going to that question, I wanted to make that from your side only. Now tell me how many chiral carbons are there in the given compound. Just look at this carbon, does it contain 4 different groups? No, this is a methyl now, 3 hydrogens are same, it's not a chiral carbon. What about this? 2 hydrogens are there. No, it should not be same, it should be 4 different groups. So this is also not. What about this? Yes, 1 alkyl group, 2nd alkyl group, 3rd one, which are ethyl, methyl, some other group, and 1 hydrogen. So this is chiral carbon. And what about this? Ethyl, some propyl and methyl, one more is, so this is also chiral carbon. Like that, we need to identify number of chiral centers. If there is chiral center, we may expect it to be optically active, but not all the times. Okay, why I am saying not all the times? If that molecule contain any plane of symmetry, listen these words. Even though it has chiral centers, if the molecule contains plane of symmetry or center of symmetry, then molecule becomes optically inactive. So what is the first thing? Identify its chiral centers. If it is having only 1 chiral center, definitely it is optically active. If it has more than 1, like 2, 4, like that if we have, it contains any plane of symmetry or center of symmetry, then optically inactive, or we can say achiral. Optical inactive you can use. Okay. Now look at this question which is asked. Which one of the following compound is the simplest alkene that is optically active? Means what is the thing I told you? Consider chiral centers. After looking at the chiral center, if the molecule contain any plane of symmetry, then optically inactive. Yes, look at this. Look at the first compound. See, 2020 it is fast. See, this has a chiral center here. This is ethyl, propyl, methyl, one hydrogen. So chiral carbon. So first one is optically active. Go for the next. This is also optically active. But in the question they are asking simplest. Simplest one means first one only, na? Or smallest, first one. Okay, and you can ignore these two options because this is not optically active methyl group. So optically inactive. Okay, this is also optically active, but they are saying hydrocarbon or simplest alkane only. It is haloalkane. See, these two are methyls only, na? And same carbon, that must be different groups, 4 different groups. But both of them are same only, so inactive. Next. And one more thing, let me go to that slide. You can see this 2024 question, number of chiral centers in the given molecule. Tell me, easy. I know you can able to answer this. Tell me fast. Done? See, look at this. Is this a chiral? 1. What about this? That is also chiral. What about these? Chiral. And this one? No. This one? Yes. Maybe you are missing this. Okay, this one is correct. Next. This one? Yes. Is there any other centers? Any other chiral centers? Other than this? No sp3 carbon other than those? No. So it means chiral centers here are how many? 1, 2, 3, 4, 5. 5. Is this clear? Yeah. Remember this number. We'll come back to this again. There is a concept called optical activity. So this optical activity is shown by only chiral carbon containing compounds or chiral center, like those compounds only. Otherwise I will tell you, redefine this, wait for some time. See, take one white light. What do we mean by optical activity means? If you have a light, normal light, so it will be giving light in all directions. Now we'll pass this through something called chromator or nickel prism will take. That nickel prism will polarizes this light into single beam. Then we can call that light as plane polarized light. What I am saying? Plane polarized light. So when this plane polarized light is passed through the sample, I have taken sample in this cuvette tube. Through this what we are passing? Plane polarized light. This plane polarized light will be either rotated right side or clockwise or anti-clockwise. If the compound has ability to rotate this plane polarized light either right side or left side, then we can say that compound is optically active. What is optical activity? Now tell me. If the given compound has ability to rotate plane polarized light either right side, clockwise or anti-clockwise, then we can say optically that compound is optically active. Okay. If this compound is rotating plane polarized light right side or clockwise, then we can say this is dextrorotatory compound. What is that? Dextrorotatory compound. If it is rotating anti-clockwise, levorotatory compounds. So dextro you can indicate with small d or with plus. Levo you can indicate with small l. I am specifically mentioning small d, small l. You need to remember that because capital D is indicated for some other thing. Okay, small l or minus. Okay, you can remember. Okay, so now tell me, if that solution contain equal amount of mixture, like equal amount of D, equal amount of L, what happens to the net rotation? 0. Why? Because they will cancel out each other, no? So net rotation will be 0. If it is in equal amount, D and L forms are in equal amount, net rotation is 0 means optically that solution is optically inactive. So those kind of solutions are called racemic mixtures. What is that? Racemic mixture. Now separation of this racemic mixture is considered as resolution. What is that? Now you have learned 3-4 words. What is that? First, optical activity, next plane polarized light, dextrorotatory, levorotatory, and next racemic mixture is very resolution. Okay, racemic mixture is optically inactive due to what? Due to presence of equal molar mixture of dextrorotatory and levorotatory isomers of that particular compound. Okay, right. Now, for example, here I am giving a compound like this. Tell me, does it have chiral carbon? Yes, this is chiral carbon, no? Yes. If it is having chiral carbon, this molecule may have dextrorotatory nature or might be levorotatory. Sir, how can we know this? Means I can place this OH group above the plane and hydrogen below the plane in this way, or the other way possibility? OH below the plane, hydrogen above the plane. So if this is having dextrorotatory property, other will be having levorotatory. For each chiral center, there are 2 possibilities. How many possibilities are there? One is dextro, other one is levo. If there are n number of chiral centers, then how many possibilities are there? This will be the case. So you can use number of stereoisomers with n chiral centers is equals to 2 power n, where n indicates number of stereo centers or chiral centers. You can say stereo centers or chiral centers. Okay, for this molecule how many? One stereo center, 2 power 1, one is D form, another one is L form. Is this clear or not? Up to here you have studied very basic things. Okay, now at each chiral center we need to indicate its configuration. There mostly the question is from this configuration concept only. So we are going to learn something called R and S configuration. What is this? RS configuration. This is also called as absolute configuration. What is that? Configuration. If you see in biomolecules, especially when you study glucose, fructose, all these things, you are going to use D-fructose, D-glucose something. There is no relation between this DL and this RS. Okay, that DL configuration, capital L will use there. For amino acid you will use L configuration, capital L. For carbohydrates you will use D configuration, S most of the cases. Okay, because generally naturally occurring carbohydrates are there now, those are having D configuration, and natural amino acids L configuration. Okay, so now what happens, that is relative configuration. What I am saying, it is, what is that relative configuration? First we will have some clarity over relative, then comes to this absolute first. See, I am taking glyceraldehyde. What is the formula of glyceraldehyde? You can write OH. This is a Fischer projection of glyceraldehyde. In this glyceraldehyde, in Fischer projection, OH side, right side na, then you can say this is D-glyceraldehyde. If OH is left side, with respect to this glyceraldehyde as a standard reference, we are giving DL nomenclature for other carbohydrates or amino acids or whatever might be. Okay, if electronegative, in case of amino acid we will be having NH2 group now. If NH2 group is right side, capital D, left side. Is that clear? Now, can you give configuration for this? Tell me. See, below 1, see, we need to number it from above side because carbohydrate, like aldehyde is priority group, so come from here 1, 2, 3, 4, 5. After this, generally DL nomenclature is given to the bottom chiral carbon, whether if it is right side D, if it is left side L, okay, by looking at the bottom chiral center. But if you want to indicate for all chiral center, what are the DL nomenclature? Tell me. 2, D, 3, L, 4D, 5D, like this. I hope this normal DL nomenclature is clear. This is what? Relative. Why relative? Because it is relative to the D-glyceraldehyde. Now what we are discussing here? RS nomenclature. So this is absolute nomenclature. It means this nomenclature projection like indication RS nomenclature is given based on standard rules given as CIP rules, Con, Ingold, Prilog rules will say. Okay, as per these rules, CIP rules, as per CIP rules, you need to prioritize the attached like chiral carbon containing groups. All these groups are there now. We need to prioritize them based on atomic number. Based on what? Prioritize the attached groups based on atomic number. Sometimes atomic number is same. Consider mass number. What is the second one? Consider mass number. So when it will be possible, sir? When we have isotopes. Hydrogen deuterium is there, which is having same atomic number, na? So mass will be more for, so that will be prioritized one. Okay, first consider based on atomic number Z. So tell me here in these two projection, which is more priority as per atomic number on this carbon? Tell me fast. Without wasting time, I just want to end up this. Tell me, OH, oxygen atomic number is more, so 1. Hydrogen, methyl, ethyl. In this case, bigger the group, carbon, carbon both sides. But again 1 mole carbon, here all hydrogens, bigger number, bigger size. So 2, this is 3, 4. So now you need to go from 1 to 2, 2 to 3. So how this direction is, like clockwise or anti-clockwise? Clockwise. When we are indicating in this way, clockwise direction, and see, if priority groups are in clockwise direction and least priority on dashed line, then what is that? Clockwise direction I am saying, and least priority group must be on last line. Then this will be R configuration. What is that? R configuration. Below the plane. Least priority group should be on below the plane, like dashed line. And if it is anti-clockwise, following same rule, if it is anti-clockwise, then it will be S configuration. Sir, what if that least priority group is not below the plane? Then configuration becomes opposite. What I am saying, if the least priority group is on above the plane, in that case, what happens to the configuration? R becomes S, S becomes R. You can add that point also. And if least priority group is on solid line, then above configuration becomes opposite. R becomes S, S becomes R. Now try to identify RS nomenclature here. Least priority below the plane, clockwise direction, so it is R. Same I want for this. 1, 2, 3. So from here to here, S. Have you seen, by changing these priority groups, I mean above the plane, below the plane, their configuration become opposite. So now these R and S compounds are called as enantiomers. What I am saying? So there is a new term now. What is that? Enantiomers. So is this clear or not? Identifying RS nomenclature. Okay, I will show you some compounds. Wait. RS nomenclature here it is clear na? In this thing clear na? So let me give you, see this is wedge dash representation. What is that? Wedge dash representation. One more representation, Fischer projection is there na? There are a lot of questions on Fischer projections only. Same rules, it almost looks same only. See I am writing CHO here and here one hydrogen and one OH and one CH2OH. 4 different groups are there or not on this carbon? Yes. Assign their atomic based on their priorities. OH is 1. After this carbon, look at this. This is C double bond OH. This is single bond OH. So if this is having multiple number of bonds, write it in this way. See, oxygen. To this carbon, how many bonds are there with oxygen? 2. It means you can make 2 oxygens. To this oxygen, how many carbons attached? I mean 2 bonds are there now, so already 1 bond, 1 more like this. You need to write in that expanded manner. So that which will be more priorities out of these 2? Above 1, aldehyde group, so 2. And this will be 3. So from where to where I go? C double bond O is there now. 2 O's we need to connect. 2 oxygen also carbon bonded with 2 sides now, so you represent that 2. Yeah. If it is triple bond, again repeat the same process. Okay? Because first you need to look for that atom which is directly attached. This is carbon, this is oxygen, which is more prioritized. That's it. After this, go for the next atom. If these atoms are same, go for the next atoms.
So if it is for triple bond, let C 3 oxygen.
C triple bond N I have. Tell me fast. C N N N, and to this nitrogen 3 carbons. 1 carbon already there, 2nd carbon, 3rd carbon. Okay, clear? Right. Now tell me here how it is. Clockwise direction. Clockwise direction we have. Clockwise direction means generally we know R. But again remember, least priority group on vertical line if clockwise R configuration. If anti-clockwise S configuration. If least priority group is on horizontal line, configuration becomes opposite. If least priority group on horizontal line, configuration becomes opposite. So now tell me, this is clockwise now. Clockwise, but least priority is on horizontal. So clockwise means R, but least priority is there, so it becomes S. Is this clear or not? Directly we'll go to the questions first. Tell me. Answer me this first. Choosing the correct absolute configuration of the following compounds. Tell me whether this first carbon is chiral. No, because 2 hydrogens are there. Ignore that. Second carbon is chiral. Identify fast. So those who are in online live session, who are watching through YouTube, you can also express your answer in the chat box. Look at this, bromine will be highest priority, 1. Bromine is 1. And the next, 3rd group, this one is 2, this will be 3 and 4. So from where to where? 1, 2, 2, 2, 2, 3. Clockwise, but least, it means, clockwise means R, but least priority is there on horizontal, so becomes S. So 2S, and now tell me here, 1, 2, 3. It is clockwise, generally R, but least priority on horizontal becomes S. So 3S, 2S, 3S, that's it. Very simple now, nothing to do, okay, right. Look at this question. The 2 compounds given below are, again, we'll come to these terms you need to know, na? Just wait for some time. I don't have time. Okay. Identify this first of all. We will come back to the RS nomenclature again. Does it optically active or inactive? First of all, forgot about the question. See, if you see for chiral centers only, all carbons are chiral centers only here. But what I told you, chiral center is not the ultimate criteria, I told you. If it contains plane of symmetry or center of symmetry, optically inactive. If I pass a plane like this, we can't divide this into two equal halves, so there is no plane of symmetry. But if this is a center, from exactly, if I go above direction and exactly back, we have same groups. Center of symmetry is there, and here also methyl, same groups, hydrogens. Center of symmetry is there or not? So molecule is optically inactive. It is because of having center of symmetry, second option. Clear? Yes, first.
In this question, if we take any carbon, how can we say that it's optically active because it has the same two compounds?
Once again?
Like a tried carbon should have 4 different groups attached to it.
Yes.
But here, if we take any one carbon, it has two.
Let me take. First of all, this question is clear, na? As per whatever they are asking. Okay. Tell me, what is your question? Let us take this.
It has CO2H and
H.
And then two different.
These are there. What you are asking now?
Both are same.
Both are same, but here you can give RS nomenclature there if you want. Again, see, this is optically inactive. Forgot about the molecule. I mean, optically inactive only. We are not considering. But in case if you want whether these groups are same or not, if you want to find, give RS nomenclature here and also here. If both are R, if both are S, and you can also find it here. I mean, first of all, you find it here. If both are R, both are S, that is, this chiral center is not optically active. If one is R, one is S, then it is optically active. If it is R, if it is S, priority is given to R, not to the S. Is this clear? So if it is 1, then second priority goes to the R configuration, then third one for S, like that. Clear now? Any confusion here? You are asking this one only now. Yeah. Okay. And remaining questions are also there. We will discuss in the next class. Okay. But see, you can able to solve these questions. You just try. If not, anyways, tomorrow we will be continuing on this stereochemistry part only, whatever the things are there. Okay. This chapter is actually full big chapter it is, but we can go with PYQs so that it will become very easy for us. Okay. So very simple questions are there in your exam. Anyways, it will be done very smoothly. Okay. You can practice few questions. If any doubts are there, you can ask me. And you can solve IIT JAM chemistry questions directly if you want. Stereochemistry, IIT JAM chemistry or CUET papers you can solve, and if you have doubts you can come to me. We will solve together. Oh man.